Everyone, welcome to Chapter 5, Thermochemistry. So this is going to be the next chapter that I teach you out of the textbook that I use. And let's get started with Thermochemistry Introduction. So our society depends on energy for existence, and with the exception of the energy from the sun, most of the energy that we use in our daily lives comes from chemical reactions that are taking place. For example, the combustion of gasoline in order to drive our cars or heat our homes, production of electricity from coal to charge our phones, heating homes by natural gas, and even batteries to power our electronic devices such as our phones, such as our gaming systems, our remote controls. So all of these require energy. And what exactly is energy, though, and what principles are involved in its production, consumption, and transformation from one form to another? Why are we able to take coal and gas and transform it to give energy to power our homes or cell phones? So this is supposed to be though. Okay. So in this chapter, we're going to begin to explore what energy is and the different changes that it can undergo. And there are two key words that go along with this chapter: thermodynamics, which is just the study of energy and the transformations. But we're going to specifically delve into thermochemistry, which is the relationship between chemical reactions and the energy changes that involve heat. So does it lose or gain heat or energy? The first part of this section is called the nature of energy. So that's what we're going to focus on today, and that's what your worksheet's going to be on. What is energy? Well, it's the capacity to do work or transfer heat. Now that we've used those two words, let's actually define those. Work is the energy used to cause an object to move against a force. So we're going to learn coming up that work is going to be force times distance. Heat is the energy used to cause a temperature of an object to increase. So it causes a temperature change. Before we get into energy, we want to first talk about the different types of energy or the different states of energy that molecules and atoms can have. So this you're going to find on your homework. There are two types. The first one we're going to talk about is kinetic energy. So kinetic energy is the energy of motion. So I'm going to go ahead and star that. Objects, whether they are baseballs or molecules or even at the nuclear level with electrons and protons, all of them possess some kind of kinetic energy. All these particles are moving. And kinetic energy, which is labeled E to the lowercase k, depends on mass and speed. So V stands for speed. We're going to be using this equation, 1/2 mass velocity squared, and you're going to see it on your homework, and you're going to have to use it as well. So I would go ahead and write that down and star that as well. Some things to know about this equation in terms of kinetic energy and how it relates to these two different properties. Kinetic energy increases if you increase the speed. And then kinetic energy also increases with increasing mass. So as you increase the mass, usually it speeds up as well. Oh, I also add that's if velocity is constant. So as long as you don't change the speed of something. Okay. The second type of energy is potential energy. Now, potential energy is described as the energy an object has based on either its composition or the type of bonds that it has, or its position, such as relative to the ground. We like to call this stored energy. A good example of potential energy is the energy stored when you stretch a spring or a rubber band. When you release it, it gets rid of its stored energy and becomes kinetic energy. A weight held above your head has kinetic energy based on the position, or different chemical bonds have stored energy and they're ready to release it whenever you break those bonds. Now, potential energy can be converted into kinetic energy. Both of these go hand in hand. If you have a bicycle at the top of a large hill, it has a pretty big potential energy based on how high it is above ground. But as soon as you start riding that bicycle down a hill, the potential energy is going to start decreasing because you're going to get closer to the sea level, and the kinetic energy increases because the bicycle is starting to move. So now we're going to go into a little bit about energy and the units that we use for energy. So the SI unit for energy is called the joule. It's represented by a capital J. To break it down, 1 joule equals 1 kilograms. This little line means times meter squared divided by second squared. Now, joule is a pretty small amount of energy, so we love to use kilojoules. So a lot of times you're going to see a lot of things written as kg. And remember, in order to go from joules to kilojoules, you need to divide by 1,000. There are other units that we use for energy, and the non-SI unit is known as a calorie. A calorie in your textbook is defined as the amount of energy needed to raise 1 gram of water up a whole 1 degree Celsius. And so here we have a conversion of how to convert between calories and joules. So here's 1 cal is going to equal 4.184 joules. Now, we hear calorie and we associate it with food, but know that a science calorie and a food calorie are different. And they're usually indicated by giving a capital or a non-capital letter. So if it's non-capitalized, it's science. If it's capitalized, it means like a calorie in food or nutrition. And 1 capital C calorie is actually equal to 1,000 calories or 1 kilocal. Now that we learned about energy and what it is and what units that we use and different types of energy that things can possess, we need to talk about it in relation to when we're studying things. So here we're going to talk about systems and surroundings. Okay. So when analyzing energy changes, we like to focus on a limited and well-defined part of the universe. We don't want to focus on everything. We want to focus on a specific thing. And this helps us keep track of energy changes that occur. So there are 2 terms you need to know, and I would write these down. The system is the part of the universe that we're singling out to study. So are we studying the bonds between nitrogen and carbon? Are we specifically studying a specific reaction? The surroundings is everything outside of what we're studying. So some examples of these 2, if we're studying the energy changes that accompanies a chemical reaction, the reactants and products would be the system, and the container that it's in, whether it be a beaker or a cup, and everything else is called the surroundings. Now, there are different types of systems. They may be open, closed, or isolated. An open system is where both matter and energy can be exchanged. So a good example of this is if you have a pot of boiling water. Matter can escape because water can be turned into water vapor and go off into the air. And energy is also transferred because energy is going from the stove into the water. Next, we have a closed system. This is where energy can be exchanged with the surroundings, but not matter. So if I put a lid on that saucepan, I'm trapping the gas. It can't escape, but I can still conserve that energy. Energy is still able to flow in and out, considering why if you put a lid on something while it's still able to cool down. Okay. And then an isolated system is neither energy nor matter can be exchanged. Now, an isolated system is very, very hard to accomplish. The closest example I can give you, if you have an insulated thermos that has hot coffee, that slows down at such a slow rate that not a lot of energy or matter escape unless you take the lid off and you drink it and let the hot air escape. But it's the best example that I can give you. Okay. So going back to our beginning slide, we talked about energy and how it's either the company of work being done or heat exchange. So let's talk about those 2 things in more detail now that we've talked about energy, talked about how we use units, and how we observe energy through systems and surroundings. 2 ways to experience energy changes is through work and heat. An example of these 2 things is if a pitcher is throwing a baseball, work is being done to make that ball move. And then in terms of heat, if you add heat to a burner to water, it makes the water temperature rise. So if we focus on these 2 things, work, which is indicated by a W, is the energy transferred when a force moves an object, or otherwise work equals force times distance. Usually, you're given distance, but you need to calculate force. So I've also included how to calculate a force. If you don't know what a force is, it's any push or pull exerted on an object. And force is actually the mass in kilograms, so it has to be in kilograms, times the acceleration due to gravity. Now, the acceleration due to gravity we learned when we were doing our gas chapter, but if you forgot, it's 9.8 meters per second squared. Now, force and work should sound familiar to you because we did cover it in integrated science, whether you had Mr. B, me, or Mrs. Gertie. And then heat, the energy used to cause the temperature of an object to increase. So one thing to notice about heat is it's always transferred from a hot object to a colder object. Okay. So here we're going to be doing just a little bit math things because I'm going to show you some examples of how we can use what we know and this knowledge that we went over to help you guys with your homework. Here it says a bowler lifts a 5.4 kilogram or a 12-pound bowling ball from the ground. Wow, I am full of spelling mistake. Lifts to a height of 1.6 meters, which is about 5.2 feet, and then he drops it. So the first thing it wants to know is what happens to the potential energy as it's raised. Well, think about it. This is getting farther from the ground. So here, your potential energy is going to increase, especially relative to the ground. So hopefully you guys got that same answer. Part B says calculate the work in joules needed to raise the ball. So let's talk about work's equation. Work equals, and let's go back, force times distance. Well, we have my distance, 1.6 meters, but I don't have my force. So I have to use my force equation. Force equals mass in kilograms times acceleration due to gravity. Well, I have my mass in kilograms. So here, F equals 5.4 times 9.8. And then if you go ahead, you guys can calculate this. So if you do this, 5.4 times 9.8, you get 52.92. So 52.92. And force is measured in something known as newtons. Okay, so force, now that I have my force, times my distance, so 1.6 meters. You can multiply these two things in order to get your work, which is about 84.672. Now, one thing to remember about work is measured in joules because it's a type of energy. Okay. Now, let's go ahead and check the answer. Okay. Looks like we did it correctly. So, about 84.672 joules or 85 joules. Then we get our last question. After the ball is dropped, it gains kinetic energy. If all the work done in part B can be converted to kinetic energy by the time it strikes the ground, what is the ball's speed just before it hits the ground? So here we're going to have to go back, and if you look at your notes, this equation, because we have kinetic energy. So all that potential gets converted to kinetic. So that's 1/2 mass times velocity squared. So here we have kinetic energy equals 1/2 mass velocity squared. So we have to plug in what we know. So we know our kinetic energy is about 84.672. Here we have 0.5. We know the mass to be 5.4. We don't know velocity, and this is all squared. So here what we can do is we can combine like terms. So we have 84.672. If you do 0.5 times 5.4, So 0.5 times 5.4 gets you 2.7. So 2.7 x squared. If you divide both sides by 2.7, let's see, you should get 31.36 x squared. Oops, sorry. 31.36 equals x squared. If here you have an x, in order to get it by itself, you square root it. So when you square root this, the x, or the velocity, actually ends up being about 5.6. So here we have speed. So remember, speed is measured in meters per second. So about 5.6 meters per second is what your speed is for the ball if you transferred it to kinetic energy. Here's a little bit more practice problems. It says, what is the kinetic energy in joules of a mole of argon atoms moving at a speed of 650 meters per second? So here you're going to use the kinetic energy again. So kinetic energy equals 1/2 mass times velocity squared. Here we don't know my kinetic energy, so I can put an x for it. 1/2 is 0.5. And here it says a mole of argon. So in order to do this, all you have to do is look on the periodic table and see how much a mole of argon is in grams, and then make sure that you put it in kilograms because mass has to be in kilograms. If you were going to look on the periodic table, you're going to see that the molar mass of argon is 39.948 grams. In order to change that to kilograms, you want to divide by 1,000. So divide by 1,000. And that gets you 0.039948 kilograms. So I can plug that in there, 0.039948 kilograms. My speed is 650. And then if we square that all, that gives me my kinetic energy. So if I go ahead and do that all, and you equal this out, you're going to find out that x equals 8,439.015 joules. And if you wanted to change that into kilojoules, you could also say that it's 8.4 kilojoules because you just divide by 1,000. Now, how do we convert this energy to calories? We have to think back to our notes when we saw the conversion. So let's go back and find that conversion. Here, 1 calorie is 4.184 joules. So let's write that down. 1 calorie equals 4.148. Let's double check that. 184. 184 joules. So we just set up a conversion. Here, I know this is my joules. So 8,439.015 joules. In order to cancel joules, I put it on the bottom. I want calories on top. So 1 calorie, it says over here, is 4.184 joules. Now that I've set up my conversion, it tells me to divide these two numbers. So if I take that number and I divide it by 4.184, you get about 2,016.97 calories have actually been used, and that's how much energy is in this argon. And if we think about human calories, that's only about 2 human calories, so it's really not that big. That's the end of today's lesson. Let me know if you have any questions, and I hope you guys have a good day.